In the previous episode, I built an electric motor from scratch, but of course we didn't test it yet, so that's what today's video is all about. Now before we get started, here's a couple of things that I think are good to know first. So the type of electric motor that I've built is called a switched reluctance motor, which at this point I've made a whole bunch of videos about, including part 1 of this, where I built the motor from scratch. If you don't know what that is, it might be a good idea to watch the first video about those that I made, which explains the working principle, just in case you're watching this video and you're like, well, what the hell is he talking about? Another thing that's interesting is that you'll notice that in this video I focus a lot on the torque of the motor and not that much on the power output, and I have a couple of different reasons for that. So firstly, the test bench that I made is not very suitable for running motors at higher RPMs, and running at higher speeds is what you need to achieve maximum power. Another reason is that power is not a super good indicator of motor performance relative to the size. So of course power is torque multiplied by speed. So if you multiply those two, you get the power figure. So if you want to make more power, you can do it by having more torque or having more speed, or both, of course. The thing about having more torque is that it usually involves making the motor bigger, because to make more torque you need thicker windings that can handle more current, or you need bigger coils, bigger windings, or you need to increase the diameter of the motor or the length or something like that. Whereas to get more speed, there is not really such a penalty. If you want to get more speed out of a motor, you basically just need a higher supply voltage, or maybe fewer turns on your windings, and that's it. And so it doesn't really come with the same size increase. So higher rotational speed is almost like a free way of getting more power out of a motor, and it's not quite that simple, because of course there's things like eddy current losses at some point due to the higher electrical frequency. There's mechanical considerations. So okay, you can't make an infinitely fast spinning motor, but especially for lower RPM motors, more speed is essentially free power. And that's also why you can have little drone motors that are this big that can make several kilowatts of power, and on the other end you can have big industrial motors that weigh 5 or 10 kilos and make maybe a few hundred watts. That's not because the drone motor is so technologically superior, it's just because the little drone motor makes very little torque and runs at a very high speed, and that's just favourable for making lots of power in a small size. So when it comes to the size of a motor relative to its performance, I guess, power is not that good of a thing to look at, because the size of the motor is not really that closely related to the power, but much more to the torque of the motor. A motor that makes more torque is usually much bigger. So torque density, right, how much torque does a motor make for a given size, is a more interesting thing to look at. Finally, another reason I am more interested in torque in this case is because I have this electric skateboard that I want to use the motor on, which has a fixed gear ratio. It's an 18:1 gear ratio from the motor to the wheels. I'm not going to change that, so I just need a certain amount of torque from the motor for it to move the skateboard. It's as simple as that. It would be very nice to have a 6,000 watt motor, but if it does it at, I don't know how many RPM, at 0.1 Newton meters of torque, it still wouldn't move the skateboard. So I just have a specific use case which requires a certain amount of torque for it to get the job done. Right? That's another simple reason. Okay, let's get on with it. At this point, some of you might already be bored of me just talking, and you just want to see the motor actually running, in which case, of course, you could just skip ahead to the part where I start testing the motor. But I thought that it would be interesting to first take a look at some simulation results, so then we can compare the simulation results to the real world performance of the motor, which I think is kind of fun. I mean, it's not the usual person's definition of fun, I realize that. So why is a simulation so useful in the first place? Why don't we just calculate it on a piece of paper? Well, technically speaking, you can calculate how much torque a switched reluctance motor would produce on a piece of paper. You can do it using this equation. It says that the torque of the motor is equal to 1/2 times the current squared times the rate of change of inductance over angle. So realize this is not about how quickly the inductance changes through time, it's how much the inductance changes per degree of rotation of the motor. So it seems simple then, right? Just fill in these values and you calculate the torque. Easy. But the problem comes when you have to fill in the right values for the inductance. And that's not so easy. And the reason it's not so easy is because of magnetic saturation. So think about, let's say we have a coil around a piece of steel. Now, of course, if we feed current through that coil, there's going to be magnetic flux inside the steel, right? There's going to be a magnetic field. Now, if you plot out the magnetic flux versus the current, you might expect it to look something like this. So it's like a straight line that goes up. If you have more current, you also get more magnetic flux. Makes sense. And this is actually what it's like up to a point, because at a certain point, when the current goes past a certain value, the steel that the coil is wound on becomes saturated. So at this point, your magnetic flux no longer increases that much as you increase the current. And so what happens is this curve starts to flatten. Now, why does that matter? Well, because inductance is basically how much magnetic flux you get for a certain amount of electric current. So that makes it the slope of this line. Like, that's your inductance. The inductance is how steep this line is. And that means the inductance is different in this point than it is in this point. So your inductance can vary based on the electric current, and it's not just one constant value. So that brings us back to our simple motor equation. This equation works perfectly fine. It gives you perfectly good results. The problem is, you have to know the inductance, and knowing the inductance is not as easy as you might think, because of saturation. So this is where a simulation can come in super handy, because a simulation tool knows the properties of the material. You enter the type of steel that you use, so it knows what this curve looks like and it takes it into account. So I used a simulation tool called FEM to simulate the magnetic field in my new motor. Now, this is a tool that you can download for free, by the way, so please go play around with it. It's fun, in the same way that other things I've mentioned are fun. So what I did is I simulated the motor at a phase current of 20 amps, which is the current that I limited my drive to when the old motor was on the electric skateboard. And it told me that the maximum torque produced would be about 4.23 Newton meters, which is a very good number, because the old electric motor would never got past about 1 Newton meter. So it's like 4 times as much, which is a huge improvement considering the new motor is only slightly bigger than the old one. But what are we actually looking at here, right? What is this picture? Well, first of all, in the picture you can see the field lines, which represent the magnetic flux. And of course, the closer the field lines are together, the bigger the flux density. In other words, the stronger the magnetic field, basically. The colors mean the same thing. So the colors, I think greenish yellow is lower flux density, and then purple/red is higher flux density. So it's just another way of representing the same thing, but it looks better than just having the lines, right? Now, if we think about what we want to see in this kind of picture, we would want to see very, very high flux density right here in the air gap, right? Because in the air gap, that's where the torque is being produced. the stronger the magnetic field, the better. The stronger the magnetic field, the more force we can produce there, the stronger the electric motor will be. But in the rest of the magnetic circuit, so in all the steel surrounding it, the steel of the stator and also the steel of the rotor, in those places, having a high flux density is not useful. It doesn't do anything there. What it does do, of course, is it pushes the material into saturation. So, ideally speaking, you have as low flux density as possible in all of the steel, and then very, very high flux density right in the air gap. Now you can see that in my motor that is not quite the case. There is quite a lot of reddish purple going on, and that brings me specifically to a comment from someone who mentioned that I made the back iron way too thin. I should have made the back iron thicker, because that would make the magnetic reluctance lower, and of course the motor would make more torque. And so that's what I did. I made another simulation where the back iron was way thicker, like 3 times as thick, and it got a little bit more torque, but not actually that much. I think it went to about 4.33 Newton meters. So I gained about 2 or 3% extra torque by doing this. And so the thing here is that technically that's good, but what did it cost me? Well, the simulation tool can also calculate the volume of the material used, and it turns out we need like 50% more steel in the stator, which also makes the stator 50% heavier. And I think the stator is a little over half the weight of the whole thing, so that would make the motor like, I don't know, a third heavier or something like that, like very significantly heavier. So it would require a lot more material just to gain 2 or 3% extra torque. And that's because, okay, yes, thicker back iron will lower the reluctance, reduce the saturation, whatever, but the majority of the reluctance is still in the air gap. And that's so much bigger than the reluctance of all the steel, that adding more steel to, let's say, the back iron, but also the rotor or the base of, the base of the teeth, for example, it wouldn't be as useful as you think. Like, it would make more torque, it would help, as you can see. But it doesn't make as big of a difference as you might think, and it does actually cost a lot of extra material. So all of this is a trade-off. You do something here, and you get something back, but you also have to pay for it in some way. And so the nice thing is you can play around with this, and you can try and optimize away at this and make better motors, of course. So I'm not saying that my design in any way is the perfect or ideal or optimal design. I think a lot of people could take this and tweak and tune it and probably get better performance for the same or less material. And actually you can do that because the CAD files are going to be online, so you can download them, you can throw them into the simulator, you can have a go at this yourself, which I think is once again quite fun. But anyway, that's enough messing around in the simulator. Let's move on to the real thing. Of course, before I could actually run the motor, I had to connect it to my electronic driver, the same one that I used for the previous motor. The setup process was also very similar to the previous motor. So if you want to know more about how I did that, you could just watch that previous video, because it's the same here. And then I was able to spin it up for the first time, and I noticed that it ran very smoothly. It also turned out to be pretty balanced. I didn't really have to grind off material off the rotor to get it balanced, so that was nice. And of course I did the manual torque test that you always do when you first try out a new motor, see if you can stop it with your fingers. And that turned out to be significantly harder than I thought. The motor had quite a bit of torque. Well, okay, as far as my fingers can produce a significant load, right? But even at very, very low throttle, it would produce plenty of torque that I could not stop it, so that was a good sign. So at this point I started assembling my test bench, which is a modified version of the test bench that I used before. So in this version, I removed the brake disc-like thing, and instead I just have a smooth shaft. And then what I could do is I could clamp down vice grips onto the shaft with a bit of timing belt as a friction material in between. It's a super simple setup. The shaft rotates, the vice grips are gripping onto it, and it applies torque to the vice grips, and then the other end of it can push down on, in this case still, the kitchen scale, of course. And now it was just a matter of running the motor and seeing what it would do. Immediately got up to 1 Newton meter just fine. Like 1 Newton meter, which is about 400 grams on the scale at this distance, was no problem at all. We could comfortably do that. The average phase current was about 3 amps during this test, which means the actual current through one phase while it's on is probably around 10 amps, so that's well within the comfort zone of both the motor and the driver. Now this was already excellent news because the previous motor could actually move the skateboard, and its absolute maximum torque that it achieved for maybe 10 seconds at most was 1 Newton meter, and this new motor was already easily doing that continuously while running. So at this point I started increasing the grip on the vice grips, and I was able to get the torque a little bit higher, but at this point the test setup started falling apart. I don't know if that's the right wording. The problem is I'm using this springy coupling that I shouldn't have used to begin with, but it was what I had laying around. I used a springy coupler between the motor shaft and the test setup, and that combined with the torque ripple of the motor caused the whole thing to shake violently and sort of smash down on the kitchen scale, which isn't mine by the way, so that's a real problem. So I decided that for higher torque values I needed to change the setup. So what I did instead is just clamp down the vice grips directly onto the shaft of the motor itself, which, because it's a D-shaped shaft, I can't actually run it while doing that, so I just have the vice grips completely clamped down so the motor cannot actually spin, and we just measure the stall torque instead, which I guess is not as satisfying as seeing it actually run, but whatever, it's still the maximum torque. So with this new setup I increased the throttle, and I got up to about 1200 grams on the scale, which translates into about 2.7 Newton meters of torque before I ran into my 20 amp current limit. So clearly the real world doesn't quite match the simulation, because the simulation told us we'd get 4.23 Newton meters. My two theories that I have about this are that either the type of steel that I use is not quite that I chose in the simulator. So in the simulator I chose, I think it's called 1010 steel or something like that. I'm not a steel guy, I don't know. And the stuff that I made the motor of is called DC01, which according to what I did like Googling research, right? I was going to use the word research. According to some quick Google searches, DC01 was pretty similar to the type of steel I chose in the simulator. The simulator didn't include DC01, right? That's why. So it's possible that I wasn't quite right there, and DC01 is actually a little bit worse than what I told the simulator I was using. That's one theory. A more likely explanation, though, is that the size of the air gap in the actual motor is just a bit bigger than the size of the air gap in the simulation. In reality, of course, I did a bunch of sanding and a tiny bit of grinding to make everything smooth and nice. And of course, there is a bit of tolerance on the laser cutting process itself too, like from the manufacturer. So the air gap in reality is probably quite a bit bigger than the air gap in the drawings. And I think that's where the biggest difference between real life and the simulation comes from. So I was quite pleased with 2.7 Newton meters. I mean, that's plenty for moving the skateboard, and it was still comfortably doing it. Like, the windings were still not getting very hot, because again, the wire gauge is now much thicker. But I still wanted that 4 Newton meters, so I just decided to increase the current limit. So I just changed the software a bit and changed the current limit to 30 amps instead. I was like, well, what the hell? It's probably fine anyway. And then this happened. 1900 grams on the scale, which, if you do the maths, is a bit over 4 Newton meters of torque. Now, we've been talking about these torque numbers for a little while now, and you've seen the numbers on the scale, but for me at least, getting an intuitive idea of what like a Newton meter of torque is like is pretty difficult. At least it was until I started doing this kind of testing. So here's a little clip that kind of shows you what sort of torque this is. So 1 Newton meter of torque sounds like a relatively small amount, and it might be because, you know, anything is relative. It depends on what you're comparing it to. But it actually is quite a bit more than a lot of people think it is, which can be seen if I try to turn this thing right now by hand. If I just turn on the scale for a moment, here we go. If I try to turn this by hand, it feels completely stuck. Like, I cannot do that. And if you look at the number on the scale, it goes up to like, I don't know, 200 and something, 230 grams, which is just a little over half a Newton meter. So, you know, even just half a Newton meter of torque, I cannot manually apply to this shaft. Of course, the story may be different if the shaft was a lot thicker, so I could properly grab onto it like this, or maybe I use a tool to move it. But this thing is pretty stuck. Even if I use a tool to move it, I have to squeeze down on it quite a bit to get it to move. And our electric motor here has absolutely no trouble doing that. So obviously I'm quite pleased with that part. But I think it is just interesting to take a look at, you know, 300 grams on a scale. It might not seem like a very big number, just like half a Newton meter or whatever. But if you actually see it in person, if you feel the sort of resistance that is being applied to this shaft at the moment, you realize, at least I did, that perhaps 1 Newton meter is more torque than you thought it was. By the way, for those of you interested in power, I think during that last clip, it was running at about 2000 RPM, which is roughly 200 radians per second, at about half a Newton meter of torque. So that would mean about 0.5 times 200 gives about 100-ish watts of power. So I think it's fair to say that it's at least a 100 watt motor. Maybe it's a 200 watt motor, I don't know, but it's somewhere in that ballpark when it comes to power, which again, that should be plenty to move the skateboard. So anyway, that's the performance testing that I did on the new switch reluctance motor. Of course, it's not the most elaborate or scientific testing, but I hope you enjoyed it nonetheless. I do know that it's plenty to be used on the electric skateboard, so I'm absolutely putting this thing on, and then we're going to see if we can ride around on this, and most importantly, we can see if this time it's able to go up hills and go off-road and do stuff like that. Anyway, if you enjoyed this video, maybe consider subscribing or clicking the like button, and of course, thank you very much for watching.